the clock's paradox of special relativity. Okay, special relativity. Time slows down for a moving reference frame. Okay, so two spaceships. Okay. A, the pilot of A sees B move past him. He applies special relativity and expects B's clock to be slower than his own. But B, pilot B, sees A moving past him, and the two systems are entirely equivalent, so he expects A's clock to be running slower than his own. So that is obviously a contradiction. Special relativity doesn't work. It's as simple as that. Now, proponents of the theory think that they have an answer for that, and the best exposition of it that I found is by the great Max Born. Yes, Max Born, look him up, he's well, he's dead now, but he won the Nobel Prize for quantum mechanics in 1954, and he was a great friend of Albert Einstein. And his solution to the clock's paradox I found in one of his books, Einstein's Theory of Relativity. Just got it on. I've got it on my Kindle, but that's the one there. Okay. Yeah, that's got it, hasn't it? Got reflections in there. So, how did he solve the insoluble? His solution includes accelerations, gravitational fields, which have no part in special relativity at all. They're dealt with in general relativity. In general relativity, we're told that systems that are observers who are held in a gravitational field therefore feel an acceleration, the weight of gravity, are time dilated. That's the slowing down of a clock compared to a clock which, say, is further from the source of the gravitational field. So a clock on Earth, ground level, runs slower than a clock in a plane, say several thousand feet above the Earth. Okay. So the stronger the field, the slower the clock runs in comparison. Okay, so this is Bourne's solution. I've represented it with my spaceships, again, which I like my spaceships. In special relativity, the spaceship, as I showed you before, the spaceships are very far from planets or stars, so no gravitational field is felt. Okay, so in Bourne's solution, I've represented that with my spaceships again. Well, yeah, I should have done two spaceships, but I've done one spaceship and a circular space station. Right, so we have A in the space station and B in a spaceship. So in phase one of what happens, see if you can get that. So this is A's point of view of what happens. So I've got divided it into 5 phases. So A considers himself to be stationary throughout. So he's in each phase, he's here. So he sees B in his spaceship in phase 1. B fires his engines for a very short time, turns them off and moves away. So in this phase, phase 2, Bourne says that special relativity will apply. Okay. In phase 3, B applies his engines in a reverse. I should have done that as a reverse. Comes to a stop relative to A, accelerates for a very short time back up to the same velocity that he had on his outward journey, and then continues back towards A, special relativity applying during that phase. He gets back to A and applies his engines again and comes to a stop alongside A. So A and B can now compare clocks, so they can see exactly what's happened. Now from B's point of view, over here, the same chain of events. B can consider himself to be stationary. So Born introduces a gravitational field which B resists by firing his engines in the opposite direction so that he can remain stationary. So it is A that falls in the gravitational field. A doesn't feel any acceleration, he just falls freely and moves off in that direction, during which special relativistic time dilation will occur. The gravitational field acts again in phase 3. So B maintains his position by firing his engines again. A is brought to a halt and his direction is reversed by the gravitational field and starts his journey back at the same velocity as in phase 2, we'll say. And there again in phase 5, the field acts again, and the two are B resist the field, and the two are reunited. Okay. Yeah, I kid you not. It's in his book. If you want to get the book and read it. So, where the field comes from, I don't know. Born's not concerned with that. Right, what do they find? What do the clocks read? Well, Born says that B's clock is slow compared to A's clock. Okay. And it is slow by the amount that A calculates using special relativity for phases 2 and 4. So A calculates, or it's in line with his calculation, the total slowing of B's clock is the time dilation that occurs in phases 2 and 4. Okay. So Born says that that's what the clocks read to confirm A's belief that special relativity has worked in those two phases. So what about B? Well, Born says that he accepts that his clock is slow because although he expected that A's clock would run slower than his in phases 2 and 4, he knows that he experienced an acceleration in phase 3 in the field, and therefore his clock would be slowed during phase 3. That slowing is greater, in fact it's double what the slowing he expects due to special relativity. So he accepts that his clock is slow by that amount. And so it's all good. That's all. They're both convinced that special relativity has worked. honestly, it's unbelievable. Dear oh dear. Where do I start? Well, for one thing, the first thing is that during phase 3, A obviously knows that B reversed his direction. Sorry there. So A would expect B's clock to be retarded by special relativistic time dilation plus general relativistic time dilation during his turnaround. So Bohr's introducing a complete non-equivalence between the two viewpoints there. He just leaves it out. Okay. And it's also clear that poor B, the way Bohr explains it, is he assumes that in phases 2 and 4, it must be B's clock which is retarded. So that's the paradox. In phases 2 and 4, special relativity is not working for B. I mean, Bohr is in his account, he's totally contradictory in that he says, in one paragraph he says that B's clock runs slow. In the next paragraph he says A's clock runs slow. So poor old B is, because of the way the maths work, poor old B is deceived into thinking that special relativity has worked for him. But A knows that it hasn't. Yes, it's hard to explain. It's so ridiculous, really. The other thing that sticks out is, what about phases 1 and 5? Now Bohr says that the accelerations experienced by B can be discounted. There is no general relativistic time dilation due to the accelerations there and there, because the theory says, general relativity says, that for there to be time dilation, the observers there must be distance between the observers. Well, that's disingenuous, because general relativity says that time dilation is due to a difference in the strength of the field, which occurs when there is distance between them. In this case, there is no distance between them, but there is a difference. Obviously, one system is accelerated and the other is not. So I just don't see how we can just discount those. So it's nonsense. It's nonsense. Now, the general relativistic time dilation has always got to be double the special relativistic for that solution to work. And having a suspicious mind, I wondered about this. So I looked at the maths, and the equation for general relativistic time dilation is G, the strength of the gravitational field, times L, which is the distance between two systems or two spaceships, in a field, over c squared, speed of light squared, crops up a lot, that c squared, a big number, times the time that the field acts for. Okay, so you can see that as L increases, the slowing of the clock increases. As L increases, if we go back to our example, as L increases, there we have L. That's the distance apart. The field is acting that way, so B is accelerated that way to maintain its position. The special relativistic time dilation will increase with L. Okay. So for the solution to work, the general relativistic time dilation must increase with L also, which it does. That's the equation. So as L increases, both the special and the general relativistic time dilations increase. So the general relativistic time dilation during the turnaround will always be double the special relativistic time dilation that occurs during this phase of uniform motion. That is as long as g, the field, and t, the time that the field acts for, remain the same. Okay? Now, if we double L, to L, so the special relativistic doubles, the there and back journey doubles, because we've got L in that equation, the general relativistic time dilation doubles. So that works, doesn't it? Well, if this is a gravitational field, and it stays the same in both these cases, because A is much further away, the field drops off with distance, okay? The field becomes weaker. It's the inverse square law, I think. It falls off with the square of the distance. So the effect of the field is much weaker out here than it is there. So therefore, the time that it takes to turn A around is going to be longer. So the mass T would be greater. L doubles, T is greater. So the maths doesn't work anymore. So it's very convenient that that general relativistic time dilation happens to have that as its equation, and as I say, it smells. It smells. It's a good example of what I see as some scientists, probably most scientists, tendency to, what I suspect is that they think in mathematical formula, and they lose track of what all those different symbols actually mean, and what is really going on in the equations. So that is Max Born's really quite ridiculous attempt to explain the unexplainable, solve the insoluble. The clock's paradox has no solution. Special relativity is disqualified, and it amazes me that they got away with this, that Bohr got away with this. You know, he's contrived here a thought experiment that I've just shown you, that it just highlights the paradox. It proves that it's, if you just think about it, it proves that there's no solution. The solution is ridiculously wrong. So either Max Born had something not quite right up there, a screw loose, shall we say, or he knew exactly what he was doing, and he was defending his very good friend's theory. Yeah, there's a book you can get about their friendship and the Born-Einstein letters. Yeah. Yeah, I'm speechless. It's just and they'll stick with this, they'll stick with it. You know, they think they've got evidence for it. How can you have evidence? How can you prove an impossibility? Okay, that's enough for that.